Hello there, this is Kevin. This video is being recorded as part of the virtual presentation for COLT 2023 and is meant to complement the short 5-minute virtual presentation we'll be sharing at the actual conference. I'm very excited to talk to you about our paper called A High-Dimensional Convergence Theorem for Use Statistics with Applications to Kernel-based Testing. This is joint work with my collaborators Xing, Andrew and Axel from Imperial College London. The talk will consist of two main parts. During the first part, we'll be reviewing some background in use statistics and motivate our results that describe the asymptotic distribution of use statistics in high dimensions. During the second part, we'll be looking at the implications of our results on the specific problem of kernel-based distribution tests. The setup we consider is such that we are given NIID data living in RD, where the dimension parameter d is potentially large with respect to the sample size n. Suppose we are interested in estimating a quantity, which is this expectation that we call d, and the expectation is taken over a symmetric function u of two independent data. A U statistic of degree 2, first proposed by Hoofdien back in 1940s, is exactly an unbiased estimator for this quantity. So it's given in this form with two double sums without cross terms. So xi and xj are always independent. A very brief, rough intuition of this statistic is that it carries some notion of an average distance within a cluster of data points given. And despite its early introduction, it has seen numerous applications even in modern day machine learning and statistics. One problem we'll be focusing a lot on is distribution tests, which I will be covering in the next slide. Use statistics has also seen a lot of applications in change point detection, as well as in stochastic optimization in programs where we care about interactions between two or more data points within a given dataset. Now let me motivate the problem we care about through distribution tests. So suppose we are given now n IID data points v1 to vn from P and n IID data points y1 to yn from Q. In distribution tests, what we care about, and in this specific example, this is a two-sample test, we care about testing whether P and Q are the same. Let's take the data point we've defined before xi as a pair of vi and yi. So it turns out that a suitable choice of u, which measures the degree of conformity among this paired data, could ensure that this expectation quantity equals 0 whenever p is equal to q. And there are particular ways of choosing this u such that this condition, if and only if condition, holds for a large class of distributions P and Q. I will not be going into the details of how this can be chosen, but for U chosen in a way that's related to the notion of kernels, you may see these two references for more details. Knowing a particular D that would give us a measure of whether the two distributions are the same, a standard recipe for doing statistical analysis given finite data is the following. We would form a statistic dn to approximate this d quantity, and we would seek to understand the asymptotic distribution of dn under the null. And this can be used to choose a rejection threshold such that we can achieve a given level of type 1 error. On the other hand, we also care about understanding the asymptotic distribution of dn under the alternative, and usually this is being considered with respect to a fixed q or a fixed class of q, and this allows us to understand the power of a particular given test against that class of alternatives. In particular, if these distributions are nice, for example, if they are Gaussians, where we can describe the confidence interval of a statistic under the null hypothesis and under the alternative hypothesis easily, we will be able to choose thresholds or understand the class of testable alternatives fairly easily. Unfortunately for U statistics, this is not always the case. So let's first consider the classical results. And by classical, I mean the situation where dimension d is fixed and the sample size n grows. It turns out that whether dn is Gaussian depends on this notion of degeneracy. In particular, dn is degenerate if this particular variance of a conditional expectation, where the expectation is taken over only one argument of the statistic, is 0. So if we have a non-degenerate dn, then indeed this converges to a Gaussian, and the variance is given exactly by this variance of a conditional expectation that we've shown above. And this is Hoofding's original result back in the days. When this variance is 0, then this normal limit is a degenerate Gaussian, so this limit actually doesn't hold. And it turns out that with a different scaling of the statistic, we can describe the asymptotic distribution as an infinite sum of weighted and shifted chi-squares. So this is called the degenerate limit of a statistics. Here, the limit actually involves this weights lambda case, and I'm not giving their technical definitions here, but very roughly speaking, they are the eigenvalues of a certain spectral decomposition of U. Now, what we care about in practice are finite sample results, because these theoretical results these asymptotic results only hold when your sample size is infinity. Right, so for this Gaussian limit, finite sample bounds are indeed available. So in particular, we know that the approximation error of understanding the statistic in terms of Gaussian has an error of 1 over square root n, which agrees with classical Berry-Essien bounds. And there are certain moment assumptions on this, which we'll cover later. On the other hand, for the degenerate limit, things are a bit more difficult. So results with minimal assumptions are mostly asymptotic, and this book by Surfling is usually the typical reference people go to. And just to give you an intuition of the existing results, so there's this Annals of Probability paper by Bankers and Guzay that shows that if we can guarantee that at least 9 of these eigenvalues are non-zero, then the finite sample bounds can be given with an error rate of 1 over n. On the other hand, Janusz-Kierwiecki have 2 papers that show that if we only know at least 2 eigenvalues or at least 1 eigenvalues are non-zero, then the rate substantially deteriorates. Moreover, Janusz-Kierwiecki actually conjectured that this particular rate is optimal. And the main takeaway is not the specific error rates that we are looking at, but is that for degenerate results, people have shown a hierarchy of different convergence rates, and the bounds depend on these explicit eigenvalues, and they require a certain number of them to be non-zero. This is very difficult to use in practice, because imagine if our U is certain kernels or involve certain complicated functions such as a neural network. It's not possible to understand this lambda case, and we are not sure how well this approximation error is going to behave. Now, the situation gets much more complicated when we move away from the classical regime. So imagine we are now in a high-dimensional regime, and here specifically I meant dimension d is large compared to n. Typical example is if you have 100 photos, and each of the photo would have much larger number of pixels than the number of data points itself. If we look very closely at the finite sample bounds for Gaussian approximation, i.e. these non-degenerate results, the bound will be given as something like this. So there's a term that looks like the usual Berry-Essien bound term, which I've excluded here. But there's also another term that looks at a ratio of 2 variances, and then it scales with square root n. So in particular, right, the variance in the denominator is this conditional variance that we've conditionals of standard deviation we've talked about before. And the one in the numerator is a variance of the entire U x1, x2. Now, of course, when dimension d is fixed, this is not an issue. This just scales as 1 over square root n because both momentums are constants. However, when dimension d is allowed to grow, u depends on d and the data points also depend on d. So it's perfectly possible for this moment ratio to be larger compared to square root n, in which case this finite sample bound no longer holds. In particular, this means that even for non-degenerate U statistic, Gaussianity is no longer guaranteed under high dimensions. On the other hand, for degenerate results, a similar problem occurs, and in particular, these eigenvalues that we've been talking about, they also depend on d, because they basically come from decomposition of these functions u, and it's perfectly possible for these eigenvalues to vanish for large d, which means all these eigenvalue dependent finite sample bounds no longer hold. Practical consequences of this phenomenon is that, first of all, when people derive power guarantees for tests based on U statistics, and when people do so through a Gaussian approximation for non-degenerate U statistics, those results may no longer hold. Moreover, we actually see seemingly sporadic behaviors. And in particular, there's this very surprising paper that came out back in 2015 by Ramdas and co-authors. And they are looking at basically the power of, so in one of these figures, they are looking at the power of a distribution test using a non-degenerate Dn. This is, I haven't specified this, but this is a kernel-based test, and in particular, there's one parameter, what they call gamma, which is the kernel bandwidth that needs to be tuned depending on the problem. So in particular, they are tuning this gamma d as a function of dimension d, which would determine the size of signal that your test is trying to detect, right? And what they have observed is that, well, first of all, across all choices, the test power deteriorates as dimension d increases, and that sort of makes sense because the problem in that setup becomes harder and harder. But the real surprise to us is that if you look at how they vary the bandwidth as a function of d, it seems that when gamma d crosses a certain threshold, suddenly the test powered behavior as a function of dimension changes drastically. Above this above a certain threshold, the test power is deteriorating at a polynomial rate, whereas in other cases it's dropping exponentially. So there seems to be a phase transition here, and what we are going to argue in this talk is that this is happening precisely because the non-degenerate U statistics that we are looking at is changing, that has a distribution change as gamma changes. More concretely, in our work, what we show is first of all, finite sample convergence results that are dimension-free under very mild assumptions. So we have gotten rid of the dimension dependence through the moment ratio we've seen. We've gotten rid of the eigenvalues. The asymptotic distribution of Dn turns out not to be determined by degeneracy, but by a moment ratio. And this is exactly the moment ratio that we've seen in the non-degenerate finite sample bound. The phase transition happens as this particular moment ratio varies. It turns out that if this moment ratio is asymptotically smaller than square root n, then indeed we have the non-degenerate limit, and that's a Gaussian. If it is asymptotically larger than square root n, we have a degenerate limit, which is this infinite sum of weighted chi-squares that we've been talking about. And when rho d is on the same order as square root n, we have some intermediate limit. So we have a quadratic form of Gaussians. That's roughly speaking a mixture of both terms. In our paper, we also applied the results to kernel-based distribution tests. So we have some very general results that work for MMD and KSD, and we also have a partial answer to the sporadic behavior described in Ramdas' paper. Cool. So we are now going to talk about the main results, and because the proof is really long, so I'm going to try to sketch the intuition for you and demonstrate why the results are in the form that should be. So we want to talk about the asymptotic distribution of dn, and we know that the expectation is always d, whether n is small or not. So really what's affecting the distribution is the asymptotic variance. And let's calculate that right now. So with some somewhat tedious calculations, we see that if we expand the variance of dn, which itself is a double sum, we get basically 4 summations. And we are going to get terms that involves x1, x2, x3, and x4, and by independence, these expectations just vanish. So really the terms that remain are, first of all, these expectations which has 1 repeated arguments, and the expectations which involve 2 repeated arguments. The first expectation term is going to simplify to sigma conditional, which we have talked about before, and the second one is going to be sigma full. In particular, we also see that there's a difference in the counts. There's a difference of ratio 1 over n because there are different because there are n order more copies of this first expectation compared to the second one. Now, if sigma condition dominates in this variance, it means that the variance of ux1, x2, described by the sigma full, no longer matters. We can in fact replace xi's in our U statistics with independent copies of xi primes, with subject to some cost of on the order of the variance. And what I specifically mean is that if you center this U statistic such that we have something that's mean 0, and then when we look at the randomness, we really care about the second moment. We can approximate this by either replacing the second argument with an independent copy, or the first argument with an independent copy. And the important thing is that there are indeed 2 sums here, because the variance of the original quantity comes from both variance from the first argument and variance from second argument. Having written the sum in this form, taking and asking and I guess fixing xi and looking only at the randomness of xi prime, xj prime, we could approximate inner sum with this conditional expectation. And after doing this, we are back to the situation where we have an empirical average of IID quantities, and this by central limit theorem can be approximated by a normal distribution. This is essentially the proof for the classical result for non-degenerate U statistic, and the techniques involved here are sometimes called the Hooftings decomposition or a higher projection. And if you look carefully at classical results, all the proofs are just about making these 3 approximation signs exact. Just as a sanity check, this works in particular for non-degenerate statistic if D is fixed, because in that case, this fraction here, sigma full over n minus 1, is always going to be small. And indeed, the ratio of these 2 terms matter, because that's exactly what appears in the finite sample amounts. On the other hand, if this second term dominates, then the entire argument I've said just now does not work. However, suppose we can decompose this function u as some infinite sum, and roughly speaking, you can understand this as potentially some eigendecomposition, although we are going to emphasize that this argument doesn't require lambda to be positive or phi's to be orthogonal. If we can use this decomposition, then let's plug this into the expression of our statistic. And it turns out that we can rearrange things such that we have basically the squared of the same sum and minus some offset. And the square of the same sum here can be approximated by some Gaussian variables, and then the quantity on the right is another just a offset centering kind of constant. And indeed, in the case when d is fixed, with some calculations, you can show that this expectation here is 0, and this entire quantity simplifies exactly to the weighted sum of center chi-squares. Now, if you follow the logic so far, we are going to make all these intuitions precise now. So in particular, what we've seen there is that if d is fixed, this sort of intuition captures all the existing results, but really it's not the notion of degeneracy, i.e. whether this sigma conditional is 0 that matters here. It's really the relative size of these two momentums. The result we are going to present, following the intuition we've described for degenerate U statistic, is going to rely on one assumption, and this assumption is what we call an L-nu decomposition. So we assume that there exists some nu, such that basically what this says is we can decompose the U statistic, this U, as some infinite sum, weighted sum, involving some scalar weights and some functions in L-nu. So we do not require an exact decomposition here, or almost sure. We just require this to happen in L-nu. And nu is chosen to be any number between 2 and 3 because just as very symbol, we'll see that this nu is like the moment condition that's required for finite example variance symbol, even for empirical averages. We also know that this condition automatically holds for nu equals 2 by spectral decomposition of a symmetric function in L2 with respect to the underlying data measure. And I'm not going to go into too much details here, but the important thing to note is that if you take the L2 decomposition, that gives you orthonormal eigenfunctions, and this is the kind of decomposition that classical degenerate U statistic theory uses to prove their results. We do not require orthonormality here, exactly because of the intuition I've described just now, which doesn't require orthonormality at all. The distribution we are going to compare the U statistic to is a quadratic form of Gaussians. It has a somewhat ugly formula, but let's unpack this. So the capital K is basically the truncation of the spectral decomposition I've described just now in this previous slide. We have D, which is the expectation term. We have this, and I guess the important thing to note in this formula is just there's eta I, which is a k-dimensional Gaussian vector, and everything else is just constant to scale things accordingly depending on the spectral decomposition. So this second term in particular is a Gaussian. And we have the third term, which is a quadratic form of this Gaussians, and in particular it's written in a way such that it's exactly a weighted sum of chi-squares. This is our main theorem. So our main theorem says that so long as this decomposition assumption we've described just now holds for some nu, then we can compare the distribution of the statistic Dn, appropriately normalized, to the distribution of UnK, but with the limit taking k to infinity, and the bound is given as some power of n and a particular moment ratio. We are going to unpack this a bit further. So this distance we are looking at is exactly the Kolmogorov distance between the distribution of Dn and the distributional limit of UnK. We are keeping the limit k to infinity outside the probability sign. And this is kind of important because this allows us to use an L-nu decomposition assumption rather than almost sure decomposition. So you could imagine that if we have this limit k move inside, the expression for UnK is going to be way simplified. It's just going to be a Gaussian in a Hilbert space and exactly a square of a Gaussian again in a Hilbert space. But that will require our assumption to hold almost surely. And this will turn out to be important in practice because our new assumption turns out to be much easier to verify. Apologies. Okay, and finally, this bound is dimension free under very mild assumption, because if you look carefully, right, I'm having the bounds defined in terms of these two momentums, which is looking at so sigma full and sigma cont are the things that we've described before, and M max nu is just really the L nu, the new moment version of sigma full and sigma cont, and they are given in the expressions above here. So the momentums is O1 if both of these ratios are O1, and i.e. if you are looking at the same notion of variance, the L nuth version of it and the L twoth version of it, they are not that different asymptotically. In particular, we have gotten rid of the appearance of ratios of the form sigma full over sigma cont. And this result is perhaps surprising to people who are used to looking at high-dimensional results, because usually for high-dimensional results, you would see dimension d appearing somewhere in the bound, and the bound getting worsened by dimension. The key intuition here is that the statistic we are looking at is having its output in R, and d only plays a role in the input. In other words, this d dimension is only an intrinsic parameter, and it's only affecting the distribution of the statistics through the data, and it's only affecting the bounds through the moments. We also want to comment that so typically, just as in Berry-Assin bounds for COT, we will typically have nu equals 3. The reason why we have a flexible nu here is just you can have more flexibility in your assumption. But for the typical choice of nu equals 3, this gives a rate of n to the power of minus 1 over 14. Although it looks like a really bad rate, but as we've discussed before, for degenerate results, when people have a guarantee of at least one eigenvalues being positive, they have shown a rate of n to the power of minus 1 over 12. And here we have n to the power of minus 1 over 14 without any explicit dependence on eigenvalues. Just to convince ourselves that the result we have indeed is saying some convergence, so we have a corollary that says that the rescaled statistic dn is going to converge to the distributional limit of our UNK, and under these assumptions. It turns out that we can also use our theorem to get very crude concentration and anti-concentration bounds. And basically the idea is that we can combine these bounds with anti-concentration results on UNK, which is just a quadratic form of Gaussians. These results are very crude, but they are nice in a way that they do not require the assumption that this distribution limit U exists, and it sort of gives us a way to understand where the statistic is going to lie relative to the expectation. We're also going to interpret this Gaussian quadratic form a little bit more, because what I've promised before is that we are going to see a phase transition, but our result so far is only comparing the statistic to a really complicated quadratic form. So as I've mentioned, the second term is a Gaussian, and actually it turns out that the variance it has is exactly the variance that we've seen for the classical non-degenerate limit. And comparing, if we choose to ignore the third term and compare our statistic dn to this second term only, then we are comparing dn to a Gaussian limit. And the error that it gives is exactly rho d over square root n, which is what we've seen in Berry-Essen bounds, non-degenerate bounds. If we choose to compare dn to the third term, i.e. ignoring the second term, then we are comparing to a weighted sum of chi-squares. And it turns out that the variance of this is exactly the variance of the degenerate limit that we've seen before. And what I want to emphasize here is also that this third term it's exactly the classical degenerate limit itself if sigma con is exactly 0. Otherwise, you will have slightly different weights compared to the degenerate case. So in our paper, we have also shown a result that says what's the error of comparing dn to this third term, and the bound is going to involve the error that we already seen in the main theorem, plus 2 additional terms. And here, so instead of having rho d over square root n, we have a term that involves something that looks like square root n over rho d. And it confirms what we've been saying all along. We have a phase transition phenomenon happening depending on how rho d scales with respect to square root n. If rho d is smaller than square root n asymptotically, we can just keep the second term and compare to a Gaussian. If rho d is greater than square root n asymptotically, we just keep the third term compared to a sum of chi-squares. If they're on the same order, we need to use our main theorem as it is and compare to this complicated UNK, i.e. we need to keep both of the terms. And a very nice thing to note here is when dimension d is fixed, rho d is always smaller than square root n so long as we are handling non-degenerate U statistic. So for non-degenerate U statistic, things are indeed always Gaussian. So the situation when non-degenerate U statistics has a non-Gaussian limit happens exactly because of high dimensionality. So here is just a summary of what I've described before, and I'm just color coding the different limits according to how rho d scales with square root n. Let's also look at some experimental verification. So I'm not going into details of a specific statistic we are using. You can look at our paper for that. But what we are showing here is basically we are looking at one non-degenerate U statistic, and we are comparing one case where we are living a really low dimensional regime, and then we have the blue line which describes the distribution of statistic aligning almost perfectly with the non-degenerate limit. We also have the right plot where we are in a really high dimensional regime, and you can see that the blue line is clearly very different from a non-degenerate limit, and it's getting close to the degenerate limit. I also want to note that the reason why we say degenerate gamma here is in the case when we have an infinite sum of weighted chi-squares, the distribution, the CDF, cannot be computed exactly most of the time. So usually people will resort to some numerical moment matching method, and here we are just showing gamma distribution as an example. Another interesting thing to note is that the degenerate limit, this infinite sum of chi-squares, may also be Gaussian itself at certain points. And the reason is that if you look at the infinite sum of chi-squares, so here I've rewritten it so that it's clearer what it is. These weights themselves, because they come from decomposition, they also depend on dimension d. And in the high dimensional setting, this means that the weights are dependent on n. And what we are comparing our statistic to is not just WNK, but really the sequential limit of distributional limit of taking first limit of k going to infinity and then limit of n going to infinity. It turns out that in probability theory, there's a really nice phenomenon called the false moment phenomenon, and it tells us exactly when this kind of infinite sum of weighted chi-squares may be a Gaussian. Specifically, what false moment phenomenon says is that if you look at the excess kurtosis of this term, this quantity, if it converges asymptotically to 0, then this will converge to a Gaussian distribution. And if the excess kurtosis doesn't converge to 0, then this is definitely not a Gaussian distribution. So this gives us a very nice way to know when our statistic may still be Gaussian. And in the case when we definitely do not have a guarantee or know that this WNK is not a Gaussian, then as I mentioned, there's no easy way to model CDF. But there are a lot of moment matching based methods, numerical methods around, which allows us to do this with a relative ease. Just to illustrate again when the degenerate limit may be Gaussian and when it may not be Gaussian. So here on the right plot, in particular, I want to draw your attention to the right plot, where we are looking at specifically a linear kernel with MMD. And for those of you who are not familiar with this, I'm going to talk about this a bit later on. So here the gamma moment matching method is not really performing well, but this is a case where we know exactly that these infinite sum of chi-squares really just have one term, so it's in fact a chi-square distribution, and we can see that this dn, the empirical distribution curve, is matching the one we predicted by our theory very well. And in particular, this tells us that there are situations where the distribution of dn can be very non-symmetric, and this also says something about the confidence intervals we are going to draw for this statistic, and also about how we should think about the behavior of power at different locations t. Now, finally, I want to conclude this session with a comparison to existing literature. So there are a lot of work that tries to study the high-dimensional non-degenerate U statistics. However, a lot of them are focusing on the degree of the statistic being large, which is just fixed at 2 here. Or some of them are studying a high output dimension, which is fixed as 1 here in our setting, and in particular for testing, most of the time we just care about 1D output statistic. There are also a lot of other work that tries to focus on the same problems as we do. However, to the best of our knowledge, most of them focus on deriving a Gaussian limit. And the results are often derived under very specific data models, very specific hypotheses, to be tested, or for a modified U statistic. The results we derive are finite sample bounds that hold for very general statistics, and actually the body of work that's most relevant to our work is the finite sample bounds work for classical degenerate U statistics. And as I've mentioned before, most of them have been focusing on using orthonormal eigenbases from the decomposition of the U statistic. Their bounds are dependent on eigenvalues, very hard to verify, and our results is free of all these requirements. Finally, for the remaining 10 or so minutes, I want to talk about the implications on kernel-based distribution tests. So very quickly, MMD and KSD are two kinds of kernel-based distribution tests that one could use to test either two sample tests or a one sample test. So this is the specific form they're given, and the key takeaway is both of them can be written as a degree 2 U statistic with a particular choice of U that depends on kernel function K. And I guess in the case of KSD, you also have some gradient of likelihood kind of functions appearing. Kernel K, having the structure of U depending on kernel K is really nice, because we actually have a lot of understanding of this, and this particular paper by Steinwart and Scoville showed that there exists a way to decompose K, which they call a weak method decomposition. And if you look at this definition of this decomposition, it's almost exactly what we require in the L-nu decomposition. The difference is that they actually have this holding almost surely. So to go from the almost sure convergence to the L-nu convergence that we require, you just need to add a few more moment boundedness conditions, and all of these are given explicitly in our paper. As a result, this means that our theorem applies very naturally to both MMD and KSD. Also, to note, one important thing to note that when we, in the case of say KSD, we need to modify the decomposition of the kernel. So sorry, here this should be a K. We need to modify the decomposition and append this gradient of log P functions to a decomposition. This would mean that the decomposition we require that we obtain are no longer have orthonormal functions. Under our assumption, this is completely fine. You can still derive asymptotic distributions and obtain guarantees, even though the set of functions are not orthonormal. Okay, so in the very final part of paper, we also focus on very specific examples that in particular were considered in the setup of this paper by Ramdas et al. And we try to understand in this Gaussian mean drift testing case what our result says about the test power as well as hyperparameter / kernel bandwidth choices for the test. So during some of the examples, we focus on this RBF kernel, where that we have the parameter gamma bandwidth parameter that needs to be adapted according to the dimension of the data. The very common way of choosing gamma is through median heuristic, and there have been several work that show that the median heuristic choice of gamma scales roughly on the order d. For this RBF kernel, it turns out that we don't even need to use the Mercer decomposition result we talked about before to verify our assumption. We can simply take the RBF kernel, do a Taylor expansion, and then so we expand this in terms of three quantities. The last two quantities each just involve one of the data points, and then this inner quantity we can just do a Taylor expansion, and then we will get an infinite sum of some function that involves only x and times some function that involves only x prime. So this is also a really nice thing about the assumption we use in our theorem. Because we don't require orthonormality, we do not require positive eigenvalues. Sometimes you can just do a Taylor expansion and easily verify our assumption. And this is very nice because a lot of cases, even though people use Mercer basis to prove results for kernel-based distribution tests, the exact form of the Mercer basis is not actually known. So this result gives you an alternative way to verify the assumption. In our paper, we then have two results, and they look really complicated, so I do not want to go into details of it. But the key is that, perhaps not so surprisingly at this point, the moment ratio rho d that we care about, which is going to characterize the distribution, which is going to say whether things are Gaussian or non-Gaussian, it depends on how large the signal size mu is, and depends on the choice of kernel bandwidth. And we see that in particular, the dependence of rho d on the different parameters are different depending on whether your gamma d, this bandwidth parameter, is asymptotically smaller than square root d or asymptotically greater than square root d. This turns out to be sort of exactly the threshold that the Ramdas paper was seeing. So modulo some rearrangement of definitions in their setup, the phase transition happens exactly at gamma being on the order of square root z. We also see this kind of transition in our experiment. I guess the slight difference is that they were looking at MMD under this setting, where we are looking at KSD under the same setting. We also plotted the distribution of dn over here in the case where we have fixed sample size, fixed the dimension, and we are only varying gamma. And it turns out that indeed how we vary the size of gamma in relation to the size of d changes the distribution, and in certain cases, this non-degenerate U statistic is again showing a degenerate limit. Cool. So just to wrap up this work, we have shown convergence results for U statistics of degree 2, where we allow data dimension d to scale with sample size n. It turns out that asymptotic distribution of a U statistic can undergo a phase transition from the non-degenerate Gaussian limit to a degenerate limit that can be described by an infinite sum of chi-squares, and we have also characterized exactly when that limit is Gaussian and when that limit is exactly not Gaussian. It's definitely not Gaussian. The phase transition happens depending on a moment ratio and not on the classical notion of degeneracy. And the consequence is that a degenerate U statistic can also have a non-Gaussian limit with a potentially larger variance than the one that's predicted from non-degenerate limits. And it may also have a asymmetric confidence interval. We have shown that our results naturally adapt to two kernel-based distribution tests, MMD and KSD, whose high-dimension performance has been of a lot of interest but has been really challenging to study previously. Our result also explains these complex behaviors arising from a simple application of MMD and KSD. And it suggests that in a high-dimension setting, one should pay closer attention to what asymptotic distribution that your test statistic may look like. If you are intrigued about this line of work, I'm also going to have an upcoming paper really soon that gives an unifying theory that generalizes the phase transition phenomenon we've seen here for high-dimensional statistics to a large class of estimators. And in particular, the class of estimators I am considering will include degree M U statistics, where the degree M is also allowed to be large relative to sample size n. If you are interested in this work, or if you have any questions about the talk, you are very, very welcome to contact me at the email address listed here. Thank you very much for listening.